Hello, AP Chemistry students. These are your notes for topic 8.9 about the Henderson-Hasselbalch equation. We're working towards the enduring understanding that a buffered solution resists changes to its pH when small amounts of acid or base are added. In this lesson, we'll learn to identify the pH of a buffer solution based on the identity and concentrations of the conjugate acid-base pair used to create the buffer. So to calculate the pH of a buffer, we'll utilize this Henderson-Hasselbalch equation, which you recall and is on your green sheet, is pH is equal to pKa plus the log of the ratio of the concentration of the base to the concentration of the acid. When we prepare a buffer, usually the concentration of the acid is equal to the concentration of the base. So the log of this ratio will be equal to 0, and the pH will be equal to the pKa. If the concentration of the acid is greater than the concentration of the base, then the pH will be less than the pKa. And vice versa, if the concentration of the base is greater than the concentration of the acid, then our pH will be greater than the pKa. Eventually, if the concentration of the acid and base become very different, the mixture loses its ability to function as a buffer. And so here is the point, that midpoint, where we have the concentrations equal. So if we get much more base, we'll get out of this buffering region. And if we get too much acid, we'll get out of this buffering region. So this usually corresponds, the buffering region corresponds to basically a pKa that is plus or minus 1. So let's do an example. For this first example, we want to find the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate. The lactic acid Ka is 1.4 times 10 to the negative 4. So our first step will be to convert the Ka into pKa. To do this, we'll take the negative log. The pKa is equal to the negative log of the Ka, which is 1.4 times 10 to the negative 4. Plugging this into our calculator, we'll get that the pKa is equal to 3.85. Now we're going to substitute our known values into this equation. So I'll have 3.85 for my pKa, and then the concentration of the base, that's my sodium lactate, so that'll be 0.10. And for my acid, that's the lactic acid there, so it'll be 0.12. And so plugging this into my calculator, I'll find that the pH is equal to 3.77. To calculate the pH of a weak base buffer, the Henderson-Hasselbalch equation can be easily modified to work for a buffer formed from a weak base and its conjugate acid. But this time we would calculate pOH using pKb. So we substitute these values into that Henderson-Hasselbalch equation, and then once you calculate the pOH, you use the equation pH is equal to 14 minus pOH. So here's another example. Let's calculate the pH of a solution at 25 degrees Celsius that is 0.1 molar of our acid and 0.1 molar of its conjugate base. So we'll start by converting Kb into pKb. So here's our Kb value. So pKb is equal to the negative log of the Kb, which is 5.4 times 10 to the negative 4. I'm plugging this into my calculator. I find that the pKb is equal to 3.27. Now I'm going to substitute into this equation. So I have 3.27 for my pKb, and then the concentration of my conjugate acid is 0.100, and for my base, I have 0.12. 0.100. And so 0.1 divided by 0.1, well, that's 1. And the log of 1 is just 0. So in this case, the POH is equal to the PKB, which was 3.27. Now the last step is going to be to convert the POH to the pH. So pH is equal to 14 minus the POH, which was 3.27. And so the pH of this solution is 10.73. Let's do another example. I have a 1 liter solution of my buffer, 0.1 molar acetic acid, and 0.1 molar sodium acetate. So I want to find the starting pH. To do that, I'm going to start by converting Ka to pKa. So I need to take the negative log pKa is equal to the negative log of 1.8 times 10 to the negative 5th. And this comes out to 4.7. Then I'm going to use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the conjugate base divided by the concentration of the acid. So I know that my pKa is 4.7. And then I'll have the log of 0.1 divided by 0.1. So again, this ratio is 1. 0.1 divided by 0.1 is 1, and the log of 1 is 0. So 4.7 is going to be our pH. So now, what happens to this buffer system if we add 0.01 moles of an acid? We want to find the pH of this new solution. So we'll use an ice table to find the new concentrations. So I'm starting with 0.1 mole. So this was a 1 liter solution. So multiplying the volume times the molarity gives me 0.1 moles for each. And then I have 0.01 moles of my acid. So that's how I got my initial values here. And I'm using moles because this is going to completely react. It's not an equilibrium equation. So I have to fully react all of that acid. And so as I do this, I will also subtract 0.01 moles here. And on the other side of the equation, I'm going to add 0.01 moles. So now I'll have 0.09 moles of my acetate ion. I have run out of my acid, and I have 0.11 moles of acetic acid. Now I'm going to plug these new concentrations into my Henderson-Hasselbalch equation. So pH is equal to my pKa, and the pKa I calculated before was 4.7 plus the log of my new ratio. So this is my conjugate base, 0.09. And I can use the value for the moles because, again, it was in a 1 liter solution. So this is my molarity as well. Divided by 0.11. And plugging this into my calculator, I will find that the pH is now 4.6. So this is the I do. We'll calculate the pH of a buffer solution for a weak acid, HA, if the concentration of HA is 0.137 molar and the concentration of A negative, the conjugate base, is 0.972 molar. The Ka for this acid is 1.51 times 10 to the negative fifth. So again, using my Henderson-Hasselbalch equation, pH is equal to pKa plus log of the ratio of the concentration of the conjugate base divided by the concentration of the acid. And so this will be equal to the negative log of 1.51 times 10 to the negative fifth plus the log of the ratio of the concentrations. And so my conjugate base concentration was 0.972. And the ratio or the concentration for my acid was 0.137. And so plugging this into my calculator, I'll find that the pH is equal to 5.672. Here's the we do. It wants us to calculate the Ka based on the following information for an unknown acid Ha. The pH of the buffer system is 4.219. The buffer is composed of 2.43 moles of Ha and 1.75 moles of NaA, or the conjugate base, dissolved into 1.92 liters of solution. Okay, so my Henderson-Hasselbalch equation was pH is equal to pKa plus log of the ratio of the conjugate base to the acid. Now I want to calculate Ka, which means that I need to solve for pKa. So I'm going to rearrange this equation. So pKa is equal to the pH minus the log of the concentration of A minus over the acid. And then pKa is equal to the negative log of Ka. So then, in order to get rid of this log, I'm going to multiply both sides by -1 first. So I'm going to change my signs. And then I'm going to do 10 to the power of both sides. So this 10 to the power cancels this, and I'll have Ka is equal to 10 to the power of negative pH plus the log of the ratio of the concentrations. So now let's substitute. My Ka is equal to 10 to the negative of my pH, which was 4.219. And then I'm adding to that the log of 2.43. Sorry, I need the conjugate base first. 1.75. And this is moles, so I need to divide by the number of liters. 1.92 all over 2.43 moles divided by the number of liters. And so I'm going to put this whole thing in my calculator, and it turns out that the Ka is equal to 4.35 times 10 to the negative fifth power. And that's it for your notes on lesson 8.9.